This is the first of two mathematical proofs for the fact that the Earth is round and spinning. This proof is for both curvature and rotation. To begin, let me say that, in summary, to describe this in a nutshell, this proof uses datum regarding the curvature of the Earth and its rotation to adequately predict the time differential between watching the sunset from the ground level to seeing the time of sunset from a tower's observation deck. This proof is in the form of a C++ program that I have written. It is to be posted online, and it is accompanied with documentation as well as this video. In order to save time in this presentation, we will call this proof, quote, the tower time, unquote. Like a recipe, here are the ingredients you need to determine the tower time. Number 1, the latitude and longitude of the location of the tower. I'll explain why in a moment. Number 2, how high above sea level is the base of the tower? Number 3, the height of the highest observation deck. Notice this is not the same as the height at the top of the tower. You have to use the perspective of someone standing at the highest observation deck. Number 4, the next thing you need to do is take the latitude, which you got as the first item in this list, and use this graph to determine the radius of the Earth as best you can based on the location of the tower's latitude. You see the Earth is a little wider at the equator than the polar radius. This chart represents the size of the radius and how it changes based on the latitude that interests you. The curved line denoted as R is the Earth's radius. All you have to do is pick the latitude and follow it up to the curved line denoted as R and note the number of height of the intersection with this line by references of the number of kilometers on the left. This gives you the Earth's radius that you will use in the equation. To illustrate this, using the position of the Earth of the CN tower, we use this geodetic graph to determine what the radius of the Earth, where the CN tower stands, is about 6,367.5 kilometers. Since the CN tower stands 71.76 meters above sea level, the true radius we will use for our calculation will be 6,367,571.76 meters. Another example is the Willis-Sears Tower in Chicago. The Earth's radius at this location is about 6,369,000 meters. Once you have this information, all you need to do is input the numbers into the program and it will calculate what you need. And you will also find the calculation accurately predicts reality. If by chance you find there's an error, measure more than one tower. The error percentage will match. And now I'll explain how the program works. Imagine someone standing on the ground and alongside our tower. If the Earth is round and spinning, they will see the sunset while the sun is still shining on the vast majority of the tower. And as the Earth continues to rotate away from the sunlight, there will be a shadow from our planet Earth creeping up the tower from the bottom up towards the top of the tower. Eventually, someone on the observation deck will see the sun set sometime after our first person saw it. Here is the geometry that explains how this time is determined. The circle represents the radius of the Earth at the determined amount we just explained. The horizontal red line represents the light barrier at the moment of sunset. The blue angled line represents the line on which the tower resides, and the distance between the intersection point with the circle and the red line would be the height of that tower. What we want to know is the equation for that blue line on which the tower resides. Finding and understanding this assumes that you have a fundamental understanding of algebra, geometry, and the X and Y coordinate system. I am familiar with these things, and frankly, I love this stuff. So, to continue, an X and Y coordinate system is used to represent mathematical formulas. Some formulas are circles, some formulas are ellipses, some are parabolic, and some are linear. Linear equations that intersect the origin of the matrix, in other words, point 0, 0, are of the form y equals some multiple times x. If there is no multiple, and so we have an equation of x equals y, then we have a linear line like this. If the multiple is 2, in other words, y equals 2x, then we have a line like this. If the multiple to the equation is 1/2, then the functional line will look like this. The quest is to find the right number to serve in a linear equation such that a line will form where the height of the tower up to the observation deck can be placed on the line such that the height will measure the distance between the line's intersection with the circle and the intersection of the horizontal line representative of the sunlight barrier. After this linear equation is found, and I will describe how that is done shortly, what is required next is to determine the distance along the circle of the Earth from the base of the tower to the point where someone would be standing at the intersection of the curve and the horizontal line representing the light barrier. This segment is thought of a slice of the 24 hours by thinking of the whole circumference of the circle represents one rotation of the Earth as if it was the face of a 24-hour clock. If you imagine this as a rotating circle, you can understand this progression of light as described at the beginning of this presentation. And there you have it. This in a nutshell is how the tower test proves that we live on a spinning ball. And now to explain how the mathematics are done. There might be many different approaches to providing the necessary math to solve this. I assume there is an algebraic method using differential equations by working it out, solving for x and y, to find the intersection point by using these two equations, where one is the exponential polynomial from the circle and the other is the proper equation for the line. If you do it this way, you have to solve for x and y by manipulation of the equality and substituting for x and y. This is one way to do it, but I found this to be a fairly challenging route to go. So instead, I wrote a computer program to do all the number crunching in a one-of-a-kind trial and error process that narrows down what the linear equation would be, and a unique process designed to make progressively better and better guesses through a large number of iterations. Here's how it works. It starts with a close guess for what the multiple for the linear equation should be. Then the program uses this in a mathematical formula for a line, as we have discussed already here. If the resulting tower height that would rest on this line is greater than what we know the tower height to the observation deck should be, a new equation is tested, but this time the number that represents the multiple in the equations is increased by a certain interval to give a new linear equation at a steeper angle. Then the process is repeated. This process changes the equation for the line accordingly to try to get closer to where it is supposed to be to represent the line we want for the tower height. This continues again and again until the line of evaluation steps over where it should be, and then the evaluated tower is too short instead of too tall. At this point, our interval change is reduced, and we work back the other direction, and this time the interval is used to reduce the size of the multiple. When we pass over where the tower should be again, we reduce the interval and repeat the process. At each pass over where the tower should be, the size of the interval is reduced, and as this interval gets smaller and smaller, we get closer and closer to finding the right linear equation on which the tower would be. This trial and error is tedious, and so that is why I utilize the power of computer software to do it. But it gets results, and these results match what we find when we test this in reality. The software only takes a fraction of a second to perform all of these described calculations. But for those accustomed to software development, I made a demonstration where I have put some breakpoints in the code and I have run the code through a debugger so we can watch an example of the calculations being made. And now we move on to the calculation for the actual time difference between what someone would see for the sunset on the ground versus what someone would see from an observation deck. This requires finding the distance along the circumference of the circle between the vertical line where the observer would be standing at ground zero and the intersection of the circle with the line that has now been determined by our process. And then what is required is to think of this segment as a slice of a proverbial pie chart, as if it represented a time interval of a clock, but in our example it would be the face of a 24-hour clock instead of a 12-hour clock. Finding this distance requires some understanding of trigonometry. What we're going to do is use trigonometry rules to determine the angle that we have. Explaining the fundamental concepts of trigonometry is beyond the scope of this documentation and presentation. Explaining high school mathematical concepts is not what this proof is required to do. If you are familiar with the laws of sine, cosine, and tangent, you would know that it would be easy to determine this angle. All you have to do in order to get the angle of the line is use the arctangent of x over y. This will give us the angle on the line in relation to the 90-degree angle. So of course, we would have to subtract 90 to get our angle we need. Then we have to convert this fraction of 360 degrees that we have determined to the same percentage of time on a 24-hour clock. This requires a bit of algebra. Here's a description of these final steps. In order to get our angle, we first take the multiple for the equation we have determined in y equals some number times x, and we get the arctangent of this. As an example, I'll use the data that was determined for the CN Tower in Toronto. 84.43 is the number the code determined for this. The code then takes the number and runs the math function arctan of that number to come up with a number in radians that's about 1.55895 radians. The next step is to convert this number in radians to the number of degrees by multiplying it with 180 over the constant number pi. In our example, this gives us 89.321. Of course, this is the number if the x-axis had 0 degrees, but we're using 90 degree or the y-axis as our 0 mark. And so we have to take this number and subtract it from 90 to get the proper degree. And so in our example, 0.678579 is the proper degree we use. Now comes the fun part, and like I said, this requires a fundamental understanding of algebra. First, we come up with a fraction that represents the portion of the 360 degrees that equals our answer. This fraction equates to a fraction where the numerator is unknown and the denominator is the number of seconds in 24 hours, which is 86,400. This is our denominator, and x, the unknown value that we're solving for, is our numerator. This gives us this equation. Now all we have to do is solve for x. Explaining fundamental and rudimentary algebra is beyond or below the scope of this description and documentation. Taking the equation above is easy to solve for x like so. In our example, crunching this number to solve for x gives us a little over 162.859 seconds. Dividing by 60 gives us the number of minutes. In our example for the CN Tower, our result is 2 minutes and 42 seconds. I ran the program again using input values for the Willis Tower in Chicago, formerly called the Sears Tower. The result of this is that the time difference between seeing the sunset by a view at the ground level compared to seeing the sunset from the sky deck of the Willis Sears Tower is 2 minutes and 47 seconds. This makes sense because the height from the ground to the Chicago Willis Tower sky deck is 477 meters, whilst the height from the ground to the sky pod of the CN Tower is only 447 meters. And reality reflects that this is spot on accurate. As best as I could, I called people who are associated with tourism and upkeep of these places, and they have confirmed that these are accurate results. And now let's talk about the actual source code. The complete software source code in C++ for this proof can be found at GitHub at https://github.com/zarzu spelled XARZU /tower-test. And anyone can download the whole software package for what is required to compile and run this proof. The main C++ file of interest is at https://github.com/zarzu/tower-test/blob/master/towertest.cpp. The version of the developer environment is completely free from Microsoft, and anyone can get the development environment and compiler for free and build this code into executable software for themselves. To compile and run the program for yourself, you can download the Microsoft Visual Studio Community 217 version at https://www.visualstudio.com/downloads/. And for the sake of completeness, I've included the actual source code into the documentation.